Yazdani Asrami, and I am with Applied Superconductivity Group of Electronic and Electrical Engineering Department, University of Strathclyde. And I'm going to present this today here on this topic: harmonic impacts for AC loss on HTS transformers and machines, basically for larger scale power applications. Thank you very much, first of all, indeed, for giving this chance to me to present my results. The content is going to be, I'm going to briefly introduce myself and Applied Superconductivity Group of University of Strathclyde. Then we delve to harmonic definition and sources of the harmonic in power system and also in standalone systems. And then I'm going to talk about importance of harmonic study in applied superconductivity. For sure, my talk is going to be mostly around this one. So it's not just a talk to present some results, some of my findings or something. I'm going to bring this topic to the attention of other researchers in order to, in future, look deeply into it. I'm going to present some of the results on the effect of harmonics on AC loss, and then summary and talk a little bit about future work. As I said, I am with the University of Strathclyde. I'm a postdoctoral research associate here at Applied Superconductivity Group. I got a PhD in electrical engineering, electrical power engineering. So a lot of my background is about conventional machine and conventional transformers and cables. My current research project is feasibility analysis and modeling of MGB2 superconducting electrical power machines. And my previous roles were about, I've been research assistant for almost 1.5 years at Robinson Research Institute of Victoria University of Wellington at New Zealand. And I work as a visiting researcher for ENA, for superconducting division at ENA, Italy. And I've been visiting researcher at University of Cassino and Southern Lazio. Some of my roles in the past have been related to electrical machine or transformers, so I'm not going to mention that. The previous project I've been involved with was design, development, and fabrication, electrical and thermal testing of fault-tolerant, current-limiting superconducting transformer, which was basically holding the world's longest resistance time for about 2 seconds. And I've done a lot of heat transfer. I've got heat transfer experience and measurement of heat transfer for metallic and superconducting tapes when you insulate them in subcooled liquid nitrogen. And I've done design development and basically AC and DC characterization for HTS coils for superconducting machines. And part of my study was about experimental study to compare the performance of conventional and superconducting transformers. Let me just briefly introduce my group. Applied Superconductivity Group, located in Technology and Innovation Center at University of Strathclyde. The group is leading by Professor Weijia Yuan and Dr. Min Zhang. I'm sure you all know them very well. We got one full professor, one reader, one postdoc, one molecular flow, and about 8 PhD students. The group at the university invests a lot, more than £1 million over the last 2 years for this group, and we published more than 100 papers over the last 5 years. We got a lot of experimental platforms here in this group: fault current limiter platform, a very unique AC loss testing platform for rotating machines, SMES platforms, and we have very unique helium circulation system, which is basically mimicking the centralized cooling system of an electric aircraft. And the project we cover here is from material characterization to cryogenic temperature power electronic, and myself working on material characterization and electrical machines, transformer, FCLs, and we work on flux pump, magnets, and power cables. The projects are funded by EPSRC, Innovate UK, Royal Academy of Engineering, and we got a lot of partners, industrial partners like Airbus, Rolls-Royce, Tokamak Energy, Epoch Wire, and others. Let me start with what's harmonic? I'm sure most of you guys know that because you got electrical engineering background, and even those people who works as a physicist, they know that we expect to see basically a periodical time varying sinusoidal waveform for voltage and currents in our electric circuit. If it's the case, the frequency of such sinusoidal waveform is called as fundamental frequency. Harmonics are any positive integer multiple of the fundamental frequency in voltage or current. We got some other harmonics like subharmonics, intermediate harmonics, and others which are not the integer, actually multiple of the fundamental frequency. Is out of the scope of this talk. So when we, in a real system, normally a harmonic order is superimposed on sinusoidal waveform, and the resultant waveform, like current or voltage, is going to be non-sinusoidal waveform. You see in the picture, in the top figure, you see the fundamental frequency, as well as other harmonics, third harmonic and fifth harmonic here in this case, with different magnitude of the harmonic order. And in the bottom figure, you see the resultant waveform, which can be quite distorted because of the harmonic components. But we actually define the level of the distortion by total harmonic distortion factor, which is defined for current like this equation you see in the bottom of this slide. And in the power system, in specific applications, sometimes current could be really distorted. What are the sources of the harmonics? If we talk about large scale power application, we need to look into the power grids and also some specific standalone power systems. Nonlinear loads in power grids is one of the main elements of making the current non-sinusoidal. Then nowadays we got a lot of power electronic converters around, like in industry, variable speed control drives for controlling the speed of the motors. And recently in our electric transportation system, like in high-speed trains, in electric aircraft, we got, for example, this figure here shows an internal power system of electric aircraft. So you see, this is a distributed actually propulsion system. We got generator and we got motors, and we got a DC bus over there. We use AC-DC converters to get the electrical energy and convert it to the DC voltage, and then we pick up the energy from the DC bus by another converter from DC to AC, and we feed our electric motors in there, which is going to be the case in near future, because now electric aircraft is a hot topic. So we're going to see this figure in many papers and many slides in future. The problem is all of these converters, they cause some harmonics. It can be very distorted current or voltage, or not that distorted because of the filtering or other issues, or switching and modulations and others. But definitely we're going to have harmonic because of them. Heavy industrial loads in like steel factories and arc furnaces, induction furnaces in them, because of a very transient nature of the load in them, we got current harmonics. They inject a lot of harmonics. There are active power filtering system to control that. Lighting systems like low energy consumption compact fluorescent lamps, CFLs, they produce a lot of harmonics because of the oscillator they got in them. Transients in power system, in rush currents, magnetization currents of the transformers, or any lightning or surge which can happen actually in the network, they inject a lot of harmonics in the network. So transformers, power cables, FCLs, and rotating machines, they're all going to be affected by this harmony. But what are the sources of the magnetic harmonics? Look, we want to study the rotating machine. A rotating machine magnetic field is interior for the energy transfer in electrical machines. So distribution of the coil windings. We have distributed winding in electrical machine in the stator, so that causes harmonic. Manufacturing tolerances, when it comes to the construction and assembly process, I've been working on this sort of machines. Sometimes manufacturer cannot deliver the same tolerance for different components of a machine, like a shaft or rotor and other part. And you get a little, because of different tolerances, sometimes you get a little bit of eccentricity in them. Mechanical faults, bearing can be worn, or dynamic or static eccentricity can happen in any rotating machine. Normally for cheap machine, they say when it comes out of the factory, it already got the eccentricity fault. But for superconducting machines, we need to look into it because cooling it is very difficult, and we got a lot of stuff around shafts. So it's very important to not to have this eccentricity fault, which can cause magnetic field harmony. Lack of harmonic components in magnetization current of transformer. If transformer could not draw actually a specific component in its magnetization current, that specific component will appear in magnetic field and also in the voltage. So that can cause problem for us. So why studying of harmonic is important, or how it's gonna, basically what are the harms caused by harmonics. From my master degree was on effect of harmonics on power transformers, and during my PhD I've done it for rotating machine like induction machine and synchronous machine as well, but they're all conventional. So through those experiences I can list these problems here. We will definitely have excessive loss when we have harmonics. Excessive loss means excessive heat, and since superconducting wires are or tapes are really vulnerable, sometimes you got weak point in them, and that can actually cause hotspot already. When you got harmonic, the heat distribution in your machine winding can be actually affected, and it can easily initiate hotspot. Knowing that with extra loss you get, maybe the heat transfer is not going to work that well. So hotspot problem is going to be a big problem, specifically for transformer rotating machines. For rotating machines, you will have torsion torques on the shaft, because simply because harmonic orders, different harmonic components, they got different sequence. Like imagine that some of them, they are rotating clockwise, some others counterclockwise. Sequence means that one, positive or negative sequence. So that will definitely, that order of harmonic will definitely actually produce a force, a component of force, which can make the torsion torque. Another one is thermal instability in cooling system. When you got harmonic, because of the extra heat, and then the change in distribution of the temperature in your winding, you might get a lot of loss. I will show in my results that AC loss can like increase drastically. So you need to have a cryocooler, and consider that cryocoolers for some of the components which are not considered as sensitive components can be actually not that great. And because, like for example, you use GM cryocoolers with 15 with penalty factor of 15, so you try to keep it cheap, and you don't have too many stages for that. And when the harmonic cause 3 times higher AC loss, then you might be in trouble. And then heat load estimation is very important in these cases. Let me give you an example of the electric aircraft. In electric aircraft, some of them are designed by, like the model M3X proposed by NASA, got more than 200 DC-AC and AC-DC converters in them. They cause a lot of harmonics. You have e-machine in there, cable, SFCL transformer, and this harmonic cause a lot of extra loss in all of those windings. And that AC loss will change, the non-sinusoidal AC loss will change your heat load actually in your machine. And then cooling system must be able to basically cope with this extra heat load in there. And it's very important you consider that one in your design stage. Normally I've seen a lot of people, they just consider the sinusoidal one. We have traction transformer. In traction transformer, we got power electronics converters, and that can cause extra actually loss in them. We've done some modeling and non-sinusoidal transport AC loss for machine and transformer coils. So we got we consider three different type of coils by superpower, tape, and single pancake, double pancake, and solenoidal coils, which cover basically the common coils in this sort of applications. And we superimposed the harmonic component on the sinusoidal one, and we applied it to the coils, and we tried to measure we tried to actually calculate the AC loss, non-sinusoidal AC loss in them. You see here at the bottom right, the figure shows actually the non-sinusoidal cases, non-sinusoidal currents we considered in our study. We covered THD from 5% to 40% in order to cover different type of loads in industry and also in internal power systems of electric aircrafts or other e-transportation systems. We have some interesting, we consider third harmonic and fifth because of the previous references which we have seen actually in literature. Normally, when it comes to AC loss calculation, people just pay attention to THD or harmonic order. So we have done the same sort of things. And then we found that THD can basically increase the AC loss drastically, but it depends to harmonic order. In case of third harmonic, we've seen actually a minimum at 20% THD. But for the fifth harmonic, AC loss monotonically increased versus THD of the distorted current. And interesting, the lowest AC loss we got in solenoidal coil and the highest in double pancake coil. I've worked with double pancake coil experimentally on the harmonic myself, and I inject square shape current into it. It's very difficult to keep it stable and thermally. It can produce a lot of loss in there, and because of the weak heat transfer in this sort of coils, you may get it burned, which was the case in my study. So in high power transformers design, we need to consider the solenoidal coil, because sometimes they consider double pancake. But if you know you're going to design it for like traction transformer or others, you got a lot of harmonics, you need to probably look into these results and change your idea about the type of the coil. And then we came across this question that why people, they don't consider the phase angle of the harmonic in their study. And we actually considered the phase angle, so we superimposed again, because our purpose is to characterize the loss. So we superimposed one harmonic, and we changed the phase angle of the current harmonic in order to see how that's going to affect the results. And we found that it's going to drastically change our conclusions and our findings. We consider third, fifth, and seventh harmonic, as we know the fifth and seventh are the most important components in power systems. So we considered first the lower order harmonics, and we found that, as you see in the figure here, with phase angle from 0 to 360, when we change it, AC loss drastically changes, and the profile of the AC loss is different for different orders of the harmonic. So we a little bit looked into it deeper, and we found that we see a symmetry from at 180 degrees, basically. From 0 to 180, we got the results, and from 180 to 360, we see that we get the same results within the modeling error, basically. And another interesting finding was AC loss increased by a power law against the carrying current level, against the load factor, and basically. And then when you plot the AC loss versus the THD, it's not going to be like you always get a minimum for the third harmonic. It depends to the phase angle. So, at lower phase angle, you get a minimum at 20% THD, but when you increase the phase angle, basically the minimum moves towards lower THDs, and after a while, you don't see any minimum, basically. After 90 degrees, you don't see any minimum. AC loss increases monotonically against the THD. And we've seen against other actually papers in the literature, we've seen actually a minimum for fifth harmonic as well when you consider the phase angle. But in case of seventh harmonic, AC loss is always monotonically increases. then we looked into higher order harmonics, because when it comes to, for example, power system, you have to study the harmonics below 1 kilohertz, basically orders of the 20. And we found that actually this figure at the bottom right, you see how AC loss changes. The dotted basically blue lines is sinusoidal one, and others are when harmonic is superimposed on sinusoidal. And as we see, if we behave as people behave in for a study of the conventional machines or transformers, and we just consider the harmonic with 0 phase angle, we're going to have a big error in our estimation, in our heat load estimation in there. Because for some harmonics, AC loss is maximum at 0 phase angle, for some is minimum. And another interesting issue we see is it is only for a third harmonic that AC loss could be lower than sinusoidal one. For all other orders, AC loss is always higher than sinusoidal one. And as you see here, it can be actually really high. It is more than 2.5 times. So 2.5 times higher AC loss could be achieved. And another interesting finding was when it goes to higher order harmonics, basically the AC loss moves towards actually a similar value over there. And it can be actually because of the high modulation of the non-sinusoidal current and the sinusoidal one. And as you see, we got actually a fit for maximum AC loss of each harmonic divided to sinusoidal AC loss. And if we plot that versus harmonic order, we see at higher harmonic orders AC loss going towards a constant value. And that's very interesting to have, because when you design your cooling system, it is actually a good information to have it on your study on your table, in order to know if you study, for example, if you have 30 orders of harmonic, after 20, you can basically consider a constant number for that. And it will actually decrease the complexity of the heat load calculation caused by AC loss. And another study we've done was we studied the AC loss of the tape under distorted magnetic field. And we actually mimic the same sort of study, what we have for current. And here we consider third and fifth harmonic, because in machines, normally because of the distribution windings, you get third harmonics or you get fifth harmonic in there. And they are very important to study in the magnetic field. And as you see, again, we study 2% THT up to 20%. So very low THT to very high. And in all of them, as you see, AC loss in the case of third harmonic, sometimes depends on the phase angle, can be higher than sinusoidal one or lower. And we characterized it. So we know below this phase angle, it is lower or it is high. It can be very important when it comes to the estimation of the AC loss, which I will show you in the next slide. And in the bottom figure, basically left, you see the results for the fifth harmonic. And here we show, despite some other references in the past, the results we get, the AC loss we get, can be even lower than sinusoidal one, which is that black dot line over there. And here at the right hand side, we plot the magnetic field for the third harmonic superimposed on sinusoidal, and for the fifth at different phase angles. And we show actually what we get over there is really related to phase angle as well. So in some phase angles, you got for a specific harmonic, you got the maximum magnetic field over there. That's why you get higher AC loss. And one very interesting study is, okay, we've done studied the single harmonics. How about the spectrums? We study a spectrum as well. Let's imagine in plug-in EV chargers, we got a lot of harmonics. And we have a transformer which supplied that PEV charger, which is going to be the common case in near future by the spread of the electric vehicles. And we get actually a current waveform here. As you see, we picked it up from a from a reference, and in the left-hand side, you see the figure. That's the current waveform of the PEV charger passing through the transformer. And in the right-hand side, we get the harmonic decomposition of that one, and with the phase angle as well. So 32% THD. I calculated the AC loss for that, and if you just consider the fundamental harmonic, means if you just design your transformer as they do right now for just sinusoidal one, so and then if you just go there and install it for such an application with this specific current, which is caused by PEV charger, your loss ratio is going to be, in the case of harmonic currents, is going to be 3 times higher than the sinusoidal loss. And it is when you when you consider the harmonic spectrum with every phase angle written in that table. If we do some, if we don't consider the phase angles, still we got higher AC loss, almost 2 times higher than the sinusoidal one. It's going to be a big hassle for your cooling system to cope with. Let me go to the summary. Harmonic AC loss needs to be studied, modeled, and measured. That's the main point. The main message I'm going to send to you, to researchers. Sinusoidal coils for larger scale application has lower loss compared to pancake coils in presence of harmonics. Non-sinusoidal AC loss increases drastically with increasing carrying current level of the harmonic, but the profile of it is depends to harmonic order as well as its phase angle. And at higher order of harmonics in current, non-sinusoidal AC loss would be less phase angle dependent. And the peak of that AC loss depends basically to the order, as you see in here. For some of them, it's going to be 0. For some others, it's going to be 180. Message to designer is like this. If you want to design a transformer, you should know that your design should be load oriented. You cannot just design a transformer and just install it for any other load. You need to know the profile of the load and the harmonics components out of it. And heat load estimation needs to be revised based on the harmonics. Because, for example, sometimes you choose your transformer with natural cooling, but probably because of harmonic, you have to consider the flow rate, and you have to choose a specific flow rate based on that extra loss you get out of your harmonics, or you have to choose the degree of the subcooling based on the AC loss you get out of that non-sinusoidal current. For rotating machine, designer needs to basically work closely with the power electronic experts to know what's going to be the output of the power electronic converter for that. And heat load estimation needs to be done based on that that profile, the spectrum of the harmonics. And another issue is when you don't have harmonic, probably you don't pay too much attention to mechanical modeling, but if you have harmonic, pay extra attention to that one, because torsion torque is going to be really a case. And another thing is temperature distribution modeling needs to be done in a presence of harmonic. At the moment, people don't do it in when current is sinusoidal, but they need to look into it. And our future work for us is like, we are working on MGB2 at the moment, doing all of this study, but because of the confidentiality, I did not present those results. And another issue is certainly in applied superconductivity community, artificial intelligence is overlooked. Basically, when we have a lot of harmonics, we can use artificial intelligence to estimate the AC loss for us. And we've done it already. We used actually artificial neural network in order to estimate the AC loss in presence of harmonics. And we compared it with 5 other methods of estimation. And we found that artificial neural network is giving you very high accuracy results. I would say more than 99.9 something percent. So you can rely on artificial neural network for any AC loss estimation in future. And thank you very much for your attention, and I'm open for any question.